For joining us for another keynote lecture. And so it's a big honor and pleasure to introduce Antonio Lijoi from Bocconi University in Milano. He'll deliver the talk on discreteness and dependence, and he'll tell us how the two things go together. Just a few words about Antonio's career. All of you probably know him. He has been, over the years, an incredibly productive contributor to Bayesian statistics and non-parametric Bayes in particular. Some of his papers, I think, can reasonably be called like real landmark papers that opened up the area and did things way before they were popular, like the normalized random measures, computation, like posterior simulation in those problems, mixture models with those problems, just about anything. Nested processes now, you name it. Antonio has done it way before everyone else followed. So pay attention. What he's going to tell us today is probably going to be the topic of the future. So he'll tell us today about discreteness and dependence, an effective interplay in Bayesian non-parametrics, if his slides come on. Can we please? Oh, perfect. Please, Antonio.
Thanks, Peter. Thanks for the kind introduction. Actually, you set the bar too high, so I hope I won't disappoint participants today. And actually, I want to say I'm very honored to have Peter introducing me because his research and his ideas have heavily influenced my work throughout the years. And probably this will also be reflected in today's talk. And I also want to thank the scientific committee for kindly inviting me to give this keynote lecture. It's again a great honor to be here and present this topic where I try to convince you about the relevance of discreteness of non-parametric priors and Bayesian models for tuning dependence of the observation. So I speak of an effective interplay, and I hope that the takeaway message will convince you about the usefulness of discreteness of non-parametric priors. Actually, this is a topic that has been experiencing a strong interplay also between the statistics and the probabilistic communities, and actually the developments of the last 20 years have arisen from these interactions. So the outline of the talk is as follows. I will first introduce some overview. So this will basically be known facts here on discrete priors, random partitions, and prediction. Then I will move on to the notion of dependence, which is partial exchangeability. You have seen already in quite a few talks here at this conference. And I move on to this general class of multivariate species sampling processes we are investigating, which is a very general framework mimicking in a partially exchangeable setting what we know about species sampling processes in the exchangeable case. And then I will discuss the induced dependent structures in this framework by relying on three different tools: the correlation structure, random partitions, and the atoms of the underlying random probability measures. Then I think, I'm afraid I won't have time to touch upon the last point on measuring dependence, but we'll see. Okay, so let's start with some basics of Stats 101. In Bayesian statistics, when I introduce to undergraduate students Bayesian approach, I start with this alternative framework to the classical one, which assumes IID with a known and fixed probability distribution. We introduce exchangeability. Exchangeability basically is telling us that the sequence of observations is invariant with respect to permutations, which means that the order with which we pick the data is irrelevant. Why is this so popular? Because, again, we have seen a very nice talk by Stefan Lauritsen on Monday on this, and variants of this representation theorem. The data are conditionally IID. So exchangeability amounts to assuming conditional independence and identity in distribution from some random probability measure, here p tilde, and p tilde is some distribution q, which is also known as the definite measure of the sequence, or we usually name it prior distribution. Okay, so this is one way we motivate the Bayesian approach when studying inferential problems. And in De Finetti's own words, in a paper in 1979, he argues that exchangeability is really what replaces independence with unknown probability, which he finds is a contradiction, because consider an example of drawing balls from an urn. Well, if you don't know the actual composition of the urn, it is quite sensible to think that your prediction of future outcomes of drawing balls from the urn will depend on what you have seen in the past. Whereas it makes sense to think of independence with common probability whenever you know the composition of the urn. Sorry, what's going on here? Okay. It is to be said that, when De Finetti introduced the notion of exchangeability, he was not thinking of setting up a new inferential paradigm, like the Bayesian one we all work on. But his idea was to provide some theoretical grounding to prediction, to inductive inference. So in other words, his idea is that prediction makes sense whenever you predict future facts based on past homogeneous or analogous events. And this notion of homogeneity or analogy finds a natural mathematical translation in the notion of exchangeability. And a prediction is quite natural because it emerges as a simple linear functional of the posterior distribution of P, given that we are able to evaluate it as it happens in several cases so far. Most often, Q is such that it selects discrete distributions with probability 1. And this will be the main reference of today's talk, this particular situation. And when we speak of discrete priors, of course, the most general class you may think of are species sampling processes, okay? Not actually the most general, but a very general class. Whereby you see these are random probabilities that emerge as an additive composition of a discrete component, a continuous component here, depending on H, which generates these atoms theta I. Generally, we use species sampling processes for which the sum of these Wi's is equal to 1, so we remove the continuous part, and we have a so-called proper species sampling process. And another terminology I will be using throughout the talk is this one. So a sequence of random variables is a species sampling sequence whenever it is exchangeable, and the De Finetti measure of the sequence is the law of a species sampling process. Okay. Now, what is an interesting characterization we may give? We said that exchangeability is relevant, especially if we want to motivate prediction. So what does prediction have to do with species sampling processes? Well, first of all, consider this setting where we have n data that display kn distinct values. We know that here discreteness implies ties with positive probability. And we still generate these atoms theta I from some non-atomic distribution H. We have this very popular characterization of species sampling processes given by Pittman, which basically tells us that an exchangeable sequence is a species sampling sequence if and only if we have some generalized Polya-Urn scheme depending on these predictive weights that must satisfy some conditions I'm not displaying here, okay? So you see at each step, each observation is either new with some probability depending on these predictive weights, otherwise it equals one of the already observed elements in the sample with some other probability. Here I denote it as P and Pk and J. Okay. So these collection of predictive weights are known in the literature as predictive probability functions. And what is nice about them? If you see, the Pittman's theorem is telling us that you may define a predictive rule without introducing a prior. So if you are able to specify these predictive weights in such a way that satisfies some conditions I'm not displaying here, then you can do your predictive inference without relying on any prior specification, okay? And this is very much reminiscent of Mike's talk on Tuesday, which was very much in De Finetti's spirit in this sense. So putting probability just on observables. But this is always, usually, actually, a challenging task. And you can see a couple of very nice papers here where you can find some technical details on how difficult it is to define a predictive probability functions, this paper by Fortini, Ladelli, and Regazzini, and this other by Lee, Quintana, Miller, and Trippa. So is there another way of defining a prediction rule? Well, again, the answer is positive also in this case. We may find an indirect way by using the induced random partition that here I label Psi-n. So the data basically from a species sampling sequence generate a partition of the first n integers such that any two integers belong to the same cluster if and only if the corresponding observations are equal. So you correspondingly define the distribution of such an exchangeable random partition, which depends on the cluster groups through, on the partition clusters through their frequencies. And here you have a simple cartoon to describe this situation. So when can we say that a function, depending on Kn and the frequencies of partition clusters, defines a distribution for an exchangeable partition? Whenever it satisfies these two conditions here, consistency and symmetry, okay? Consistency is obviously for infinite extendability of this sequence, the whole set of positive integers, whereas the second condition, which is invariance with respect to permutations, is obviously related to exchangeability. And if we are able to identify a function satisfying those two conditions, we can define the predictive weights by simply taking these ratios. Okay? So we have an indirect way for determining the predictive weights, which is still nice because you see the probability, the exchangeable partition probability function phi is still related to the observables. So we start with the definition of some distribution on the observables, in this case the ePPF, to induce a species sampling sequence and hence a prediction rule. Okay? So this is nice because we can assign probability to observable events or quantities. But again, it's very challenging to define an ePPF having these properties. I provide you just quickly an illustration with the Gibbs type priors that have been introduced in the probabilistic literature by Gnedin and Pittman in 2006, which are characterized by an array of weights V and K that satisfy these recursive relationships, are expressed in terms of parameters sigma less than 1, and have this product form, which all of you might recognize a product partition model with a specific cohesion function depending on these ascending factorials, okay? 1 minus sigma over nj minus 1. Okay, so if we have an ePPF corresponding to a Gibbs type prior, we have the predictive weights in a very simple form, and you see that the probability of reobserving the jth value of the sample is a function of the frequency of that specific cluster. And then we have the probability of observing a new value, which is these ratios of V and Ks again. The parameter sigma, as well known, is very important in impacting the random partition because according to its value, we have a different behavior of the number of clusters as the number of observation increases. So for instance, if sigma is negative, the number of clusters converges to a finite positive random variables. If sigma is equal to 0, we have a logarithmic increase of the number of clusters. Otherwise, with the sigma between 0 and 1, it is polynomial. And several well-known examples are under this framework. For instance, the Dirichlet process, by that particular choice of V and K. The Pitt-Manure process is another noteworthy example, which now displays a probability of observing a new value which depends on the number of distinct values in the sample. So the more distinct values we have in the conditioning sample, the larger the probability of observing a new datum, which is also sensible. And then we have this case with the negative sigma, which in the literature is probably better known as mixtures of finite mixtures, which is a mixture of uniform Dirichlet distributions with a number of components which is random with some mixing measure pi. These have been extensively used in prediction problems in species sampling, with species sampling data in Bayesian non-parametrics. We have a couple of papers where we initiated this kind of research. We have studied some frequentist properties in a paper with Pierpaolo and Igor, and then you can find a nice review on IEEE paper by de Blasi et al. In 2015. So, but you see that even though Gibbs-type priors are a very wide class of exchangeable partition probability functions, the problem is defining this sequence of V and Ks that satisfy those recursive relationships. It's far from being easy. So, in general, if one wants to start with assigning a distribution on the observables, this may be a daunting task, whereas if we start from a prior, problems considerably simplify. So if we want to be more operational, specifying a prior is obviously carries on a bonus. And how? First of all, using the prior Q, the definition of ePPF is obviously this one. But you see, this is clearly useless, okay? This is a very complicated sum. No way you will be able to compute ePPF through the definition I'm giving here. There are more convenient ways of computing this. For instance, a very convenient one is representing the ePPF as this marginalization of the space of random probability measures P whenever they have a nice probabilistic structure that arises, for instance, when they are functions of completely random measures. In this case, you really are able to provide closed form expressions of these phi kns and then induce predictive laws and generalized Polya-Ern schemes useful for Bayesian inference. An important point here is that if you define the ePPF this way, no need to check symmetry and consistency. Obviously, they are automatically satisfied, okay? So you don't need to check the validity of those two conditions. This is also another bonus. And obviously, of these, consistency is crucial for prediction and validity of inferential procedures, because if you lack consistency, you may end up doing some effective, nice maybe, but just exploratory data analysis. Okay, so this was the initial overview. Now let me move on to the main focus of the talk. That is moving from the exchangeable case to more complex forms of dependence. In this case, partial exchangeability you have already seen in other talks, as I mentioned. For instance, here I start with an example we have been working on random networks, multi-layer random networks, where data are nodes in a network that are clustered into different layers. Here we have 3 layers colored in green, blue, and orange. Nodes, each node belongs to a single layer, and there may be connections within each layer and across different layers. And you would like to cluster the nodes according to their connectivity patterns, okay? In this case, exchangeability doesn't work because you may have homogeneity within each layer, but not across different layers. So you need to look for different forms of dependence. And we applied, there are several examples that fall into this category. For instance, bill co-sponsorship in politics, where the layers are political parties. In this case, each member of the parliament is in just one party, but of course they, if we cluster individuals based on the bills they support, it may well be that a member of a party supports the bill proposed by another party, generating a connection. This is quite common in Italian politics, okay, which is probably messed up, but I guess it's not different elsewhere. We also worked on a problem in criminal networks where the layers are a main clan affiliation. And again, we have connections within each clan and across different clans. And those of you who had the chance to see Francesco Gaffi's talk yesterday, you might have seen this. And I also recommend to go to Filippo Ascolani's talk tomorrow about similar structures. So we are in a situation then when we have data that are collected under different experimental conditions. So we have different samples. In this cartoon, we have 3 of them. And what we can assume is that there is homogeneity within each sample and heterogeneity across different samples. But at the same time, we would like models that are able to capture simultaneously 2 levels of clustering. Sampling of the single groups, in this case rectangles. So for instance, the first and the third rectangle are considered as being homogeneous and clustered together, and of the observations, both within each cluster and across different clusters. So for instance, the red cluster here is shared across the 3 populations. It is important that whenever you are aiming to attain this kind of clustering across populations, you need to have a prior specification that doesn't allow to attain independence across different populations. I will remark this later. Okay, so what is then the symmetry notion we will be using? Well, we say that an array of sequences of random variables is partially exchangeable whenever its distribution is invariant with respect to finite permutations acting separately on each sequence, okay? This pi1, pi2, pij. So for instance, when we have 2 samples, if I swap just these 2 red variables that are in the same sample, then I preserve the distribution, whereas if I swap the blue and the red observation that are in different samples, I lose equality in distribution. And again, why is this interesting? Because we have a very natural extension to this setting of the representation theorem we have seen for the exchangeable case, so that the observations from the 2 samples are conditionally independent and identically distributed within each group, okay? So, and the mixing measure, the Definetti measure in this case, is a distribution on the product space of probability measures on a sample space X. So, I mean, there is this nice paper by Definetti where this is introduced, and also it's a very interesting paper because he also envisions this idea of measuring the distance of a particular prior specification from exchangeability we try to pursue. Whereas more recently there have been this contribution by Cifarelli and Regazzini that went unnoticed in 1978, where they first used this kind of dependent structure, but we all owe to the pioneering work of Steve the current use of modern dependent priors for partially exchangeable data. So what are the 2 extreme cases one can notice here? 2 natural extreme cases correspond to homogeneity, which boils down to a prior which is degenerate on the diagonal, and unconditional independence, which boils down to independence. And it's important to see that when you have independence, the observations from one sample do not impact the inferences on the distribution of the other sample. So in other words, whenever you have independence, there is no way you can build clusters that are shared across samples. So you see we have this range of possibilities between exchangeability and independence, and one would be interested, for instance, in understanding how much a prior is concentrated around the diagonal representing exchangeability, or how much it is spread out and more consistent with a situation of unconditional independence. So one way to study this is through random partitions, okay, that extend the ideas to the partially exchangeable setting of what we have seen for the exchangeable case. So suppose we have 2 discrete priors, so 2 species sampling processes. They induce on a partially exchangeable array k distinct values, okay, out of these 2 samples with sizes n1 and n2. And the respective frequencies with which these distinct values are observed in each sample are summarized by these 2 vectors n1 and n2. So nij is the number of elements in sample I that equals the jth distinct value. Having shared clusters across the 2 samples means that the frequencies corresponding to one of the jth distinct values are both positive. And again, you see this generates a random partition on the sequence of integers, of positive integers, which in this case has a partially exchangeable structure that can be characterized by this distribution pkn n1 and n2. Okay? And again, the problem is, can we identify such a distribution? Is there a way to assign it directly without using a prior, or should we use a prior? And the answer will be the latter, obviously. Also in the multivariate case. So here is the situation. So you see we're going to study joint distributions of partitions, okay, where we can have shared clusters. You see here the frequencies are both positive 3 and 1 in the two samples, or sample-specific clusters like the gray one here or the blue and the orange one here. And from this joint distribution, we can obtain the marginal distribution corresponding to the usual ePPF I've presented earlier. So if we use a prior, how would you compute the ePPF, the partially exchangeable partition probability function? You would use this crazy definition, which is, basically useless from an operational standpoint. And again, it's much more convenient to use a representation where you can marginalize with respect to the underlying probability measures P1 and P2, especially when these are functions of some probabilistic objects like completely random measures. And this has been done in quite a few papers in the literature so far, and here I'm listing just a subset. Okay. Now, what I'm going to do here then is to approach dependence considering a very general framework where the priors we will be considering are discrete and corresponding to a so-called multivariate species sampling process. And we ask ourselves whether what is the dependence that this prior specification induces on the probability measures and on the observations, both within each sample and across different samples. And as anticipated, I will analyze these two questions by relying on three different tools: the correlation structure, the induced random partition I have already presented, and the atoms of the PJs. Okay, so multivariate species sampling processes are a natural extension to the multivariate setting of the species sampling processes, whereby each PJ is represented in this form. Again, you see an additive composition of a discrete part and a continuous component, depending on this H. We will basically take only this sum of weights always equal to 1, almost surely, and we will speak of proper multivariate species sampling process. Okay? Great. And of course, similar to the exchangeable case, we say that an array of sequences, of J sequences of random elements, is a multivariate species sampling sequence if it is partially exchangeable and its definitive measure is the law of a multivariate species sampling process. Okay, so first question that we asked ourselves is whether there exists some predictive characterization for this process, similar to the one we have in the exchangeable case. And if such a predictive characterization exists, can we still recover it also indirectly through the random partition? Well, the answer to these questions are both positive again. So suppose we have two samples of sizes n1 and n2 that feature these k distinct values x1 star, xk star, with vectors of frequencies along the single samples that are denoted as n1 and n2 as usual. Then we have that this array, I focus just on the case where j is equal to, but this naturally very easily extends to a general j. We say that this array of two sequences is a multivariate species sampling sequence if and only if we can find weights satisfying some conditions I'm not reporting here, such that they give rise to this generalized Polya-Ern scheme. Okay? So we start with a theta 1 from H, and then subsequent values are from this predictive rule. involving this predictive probability function. Here I'm taking as the n+1th observation one of the first sample, but it would work also if this were from the second sample, okay? So again, if we are able to introduce a sequence of predictive weights that satisfies some conditions I'm not reporting here, basically are some symmetry conditions, we can identify a prediction rule without the use of a prior. You can find, I mean, we are working on this, so we have a work in progress with Beatrice and Giovanni and Igor, where we give this condition exactly. But it is clear if you see them that it's basically impossible to find, as in the exchangeable case, a collection of predictive weights that directly satisfies them. So one way of attacking the problem is to use the partially exchangeable partition probability function. And if this is available, well, you can obtain the predictive weights by, again, very simple ratios as displayed here, okay? And each array, xj, is marginally a species sampling sequence. So you see here we have basically two approaches, also in the multivariate case. We may start from law on the observables, like the predictive weights, or the partially exchangeable partition probability function to induce uniquely a multivariate species sampling sequence or a prior, or if you like, a definite measure on the product space Qj, or the other way around, from prior to prediction. So define a prior and then identify predictive weights and corresponding partially exchangeable partition probability function. So the first approach is very appealing, okay, because it's related only to observable quantities, but it's very challenging to implement. Whereas the second approach amounts to specifying a prior and infinite dimensional space, which in some cases has to be motivated, but it can be actually implemented. So from an operational standpoint, the second procedure is very straightforward. Okay, so once we have specified this, what about dependence, okay? And the idea then is to work out dependent structures by starting from a prior specification and investigate the prediction rule and the law of the random partitions that are induced. So in the literature, one object that has been often computed for discussing dependence is the correlation between any pair of probabilities evaluated at a specific set. There are tons of results on this object for several classes of priors. And if you go through the literature, what you learn is that typically this correlation does not depend on the specific set A at which these Pi and Pj are evaluated. So this typically leads to identify this correlation as an overall measure of dependence, okay, because it does not depend on the specific set A. So we can use it as a measure of pairwise dependence among, between the probability measures in the vector. And the two extreme cases I was mentioning at the beginning are basically induced when the two extreme cases are realized. We do have a correlation which is equal 1 in the fully exchangeable case, or equal to 0, obviously, in the unconditionally independent case. Moreover, another feature that you may see in the literature is that this correlation is typically non-negative. All the examples you may go through that are available in the literature have a non-negative correlation. So in view of these facts, we try to address some problems that we found of interest. First of all, we wondered whether the independence of the correlation from set A was something specific to this wide plethora of models we have been examining, or it is something structural for a general class of priors. Moreover, we wondered what is the implied dependence on the observables. And we also tried to ascertain whether the dependence induced among the observables is such that between observations in two different samples, the correlation may be either positive or negative, okay? Moreover, we wonder whether there are models for which the correlation actually identifies the two extreme situations of exchangeability and independence. And does dependence relate to the structure of the distribution of the underlying random partitions? And finally, we also try to address a problem related to measuring dependence, okay? Using a measure that is alternative to the correlation, okay? And such that still between 0 and 1 identifies the two extreme cases through the values 0 and 1, respectively, okay? So I'll try to provide answers to these questions within the framework of multivariate species sampling processes, and I guess I won't have time to touch upon the last point, but we'll see. So first of all, suppose we have a multivariate species sampling sequence. Can one determine the correlation? I mean, what is the form, actually, of the correlation between any two probability measures evaluated at a single set A? Well, you see, it's nothing but the ratio of these probabilities of ties, involving ties across different samples and within the same sample. So it is not surprising that in all the models we have seen, the correlation doesn't depend on the set A, because it has this structure related to the observables, and it is not even surprising that it is always non-negative. Moreover, you do have that the correlation is equal to 0 if and only if there cannot be ties across the two samples, okay? Moreover, if P1 and P2 have the same marginal distributions, the correlation amounts to this ratio between the probability of tie across samples and the probability of tie within any of the samples we are considering, okay? So there is a very neat structure that explains some of the specific findings that have been highlighted for a wide class of priors I've mentioned before. Notice also, you see that the correlation here, you see, depends only on the probability of sharing atoms, regardless of the specific value those atoms take on. And they are related also to the partially exchangeable partition probability function and the exchangeable partition probability function through these two simple formulae, okay? That can be easily evaluated. Now, if we move on to a different rewriting of a multivariate species sampling processes, where the random probability is split into two blocks. The first block contains atoms that are shared across population, and the second block includes atoms that are specific to the sample and are independent from the specific atoms of the other sample, okay? So if we rewrite a multivariate species sampling process in this form, we say that a multivariate species sampling process is regular if either there are no specific sample-specific atoms, so this term disappears, or if the weights of the sample-specific atoms are independent. Okay, so we have independent frequencies of non-shared atoms. So we have this notion of regularity we have introduced because it has some implications on the dependent structure I want to show. Actually, it is worth noticing that this structure is shared by, again, quite a few priors that are available in the literature: hierarchical normalized random measures, hierarchical pit-manure processes, nested Dirichlet process and their latent versions, GM-dependent processes. They all can be traced back to this scheme. Now, what do we have? We have that if P1 and P2, sorry, here's a typo. This should be P tilde 1 and P tilde 2, is a regular multivariate species sampling process, then the correlation is 1 if and only if they are equal almost surely, and it's 0 if and only if they are independent, okay? So we have such a characterization for the specific case of regularity. What about the random partition? Well, as for the random partition, all these models typically have a partition probability function that can be represented in a mixture form. And this lambda is either a parameter or even a more complex latent structure, okay? And this is quite frequent in several priors. So you see that for a large family of discrete priors, you can find a point lambda star in the support of the mixing measure such that the partially exchangeable partition probability function boils down to the exchangeable case, okay? And so that in this case, I'm not sure what's happening here. So in this case, if the probability mass associated to the stream point lambda star is positive, the partially exchangeable partition probability function is a mixture of joint exchangeability across the two samples, so the diagonal in the previous plot, and another partition probability function that does not correspond to independence. Because if it corresponded to independence, you couldn't have shared clusters across different samples. And there are several priors, again, that can be also traced back to this scheme. Here I recall some of them: the nested Dirichlet process and its latent version, and also the semi-hierarchical Dirichlet process by Mario, Alessandra, and Fernando. So this very neat structure, where you see then it is quite tempting to interpret pi1 as a measure of closeness to exchangeability in your prior specification. And here I will give you an example that goes under the name of hidden hierarchical process. I will briefly mention it. This is a class of priors that we try to introduce actually to address this problem of studying the two levels of clusterings I've mentioned, the one at the level of the random probability measures and the one at the level of the observations. So what we did here, we matched a nested component that typically serves as a probabilistic object for clustering probability distributions and hence samples or populations, and a hierarchical component that, on the other hand, allows to cluster observations within and across different samples. So we do have a following definition of hidden hierarchical Pitt-Manure process we have been using, whereby the PJs are conditionally on G, IID from G, which is a probability measure whose atoms are P star K, okay, probability measures themselves. The weights in this representation are weights of a Pitt-Manure process. I'm using this acronym GEM with parameters alpha and gamma to denote the Pitt-Manure process, the weights of a Pitt-Manure process. And the atoms of G are nothing but a hierarchical process, the hierarchical component I was mentioning here. And this is a hidden hierarchical Pitt-Manure process. This is a composition of random probability measures that displays some of the features I have already anticipated. For instance, here, if you take gamma, first of all, equals sigma equal to sigma 0, you have a Dirichlet process version of this process. And you see, you have this EPPF, partially exchangeable partition probability function, which again is a mixture of the exchangeable case and another extreme case which doesn't correspond to independence, and it does not have to correspond to independence, actually. This is available in closed form, and you see we also have the weights pi1, so we can tune alpha and gamma to have a prior specification closer or distant to the exchangeable situation as we like. Oops, sorry. So we have a closed form expressions of both the exchangeable EPPF corresponding to the diagonal, and also for the other extreme case, which does not correspond to independence. Because if it did correspond to independence, we couldn't have had shared clusters. We are able, obviously, now it's straightforward to compute the posterior probability of having exchangeability, so homogeneity across the two distributions, so you can cluster them together based on this quantity here, so run basically some tests. And we also studied the distribution of the number of clusters associated to this process. We have a closed form distribution for Kn that again emphasizes this composition structure between the nested and the hierarchical components. And also we have a thorough investigation of the asymptotic behavior so that we do have a polynomial increase, which again you see can be understood as a sort of composition between two levels of hierarchical processes with parameters sigma and sigma naught for having this polynomial increase whenever both sigma and sigma naught are between 0 and 1. Whereas when sigma and sigma 0 are 0, so we are in the Dirichlet case, unsurprisingly, you have an iterated logarithmic behavior, which is reminiscent of the Dirichlet process case. And now I will close with a brief hint on how one can model dependence at the level of the atoms of the underlying random probability measures. So as I discussed before, most models, all multivariate species sampling processes have correlations between pairs of probability measures evaluated at a set A, which are always non-negative, and also the correlations of observations between different samples. Correlation between observations in different samples are also non-negative, okay? Because they're related to the partially exchangeable partition probability function in the form I have displayed before. So we wonder whether it is possible to go beyond multivariate species sampling processes in order to induce some negative correlation structure. And we introduced a new class of priors that are constructed as follows. So we start with a bivariate species sampling process. So I just focus on the two-dimensional case. So we have a multivariate species sampling process, you see, with a two-dimensional sequence of atoms corresponding to the two populations. And then we take the projections of these two species sampling processes on the two coordinates, the first one and the second one, in order to introduce new probability measures. Notice that with these p tilde i's, we are inducing an object which in general it is not a multivariate species sampling process, and it is a bivariate species sampling process if and only if any of these two conditions is satisfied. G0, so which is, you see, the base measure here, corresponds to independence, or when G0 is degenerate on the diagonal. These are the only two cases for which you are back in the multivariate species sampling process case. But we want to be more general than that. And we studied here the probability of a tie within each sample, which here is denoted as beta. And assuming identity and distribution, these are equal across the two samples. And we introduced this new notion of hypertie between the two samples that corresponds to this parameter gamma, that corresponds to the case where two observations from the two samples are generated from the same two-dimensional atom, okay, for some k. Having this particular form in terms of the underlying species sampling process. What we proved is that the probability of a tie is always larger than a probability of a hypertie, which is quite intuitive. And also, equality between the two probabilities occurs if and only if we have that the weights of the two species sampling processes are the same with probability 1. Okay? So, at this point, we wonder how do these probabilities of a tie and a hypertie relate to the correlations of between observations in different samples. Well, we have the following result, where we prove that the within sample correlation exactly equals beta, whereas the across sample correlation equals the probability of a hypertie gamma times rho 0, where rho 0 is the correlation induced by G naught. Okay? So you can use rho 0 to tune the dependence of between observations in different samples. And you learn that the correlation between any two observations from the two samples may vary between minus beta and beta. So when we move outside the multivariate species sampling process case, we can attain negative values. And in particular, the absolute value of such a correlation equals beta if and only if the correlation, so G0 is the generate, so the correlation at the level of G0 is equal 1 in absolute value, or when the weights of the species sampling, of the discrete random probability measures are almost surely equal for any k. Hence, with this class, we are able to achieve what we name a full range borrowing of information property with different forms of dependence going from independence, shrinkage, and repulsion of or negative correlation. So we did apply this to a specific setting that involves, unsurprisingly, always completely random measures. Okay, so we took bivariate completely random measures and then their projections to induce probability measures P1 and P2 to have a prior that we name n Furby prior. And of this, we have been able to determine the predictive characterization, okay, where you see we have these three, we have a mixture of, this should have been H, sorry, so the prior baseline, the observations of the second sample, and this is a dependence on the observations of the second sample through the conditional distribution of the first coordinate given the second coordinate with respect to G0. And a similar prediction rule holds true for the second sample. And so we have this very nice structure. But again, we started from the definition of a prior to obtain all this, and we also have some posterior characterization. And you could, I mean, those of you who have attended Beatrice's talk on Monday have probably, I've seen this in much more details. And then I don't have time to touch upon the measure of dependence, though those of you who have attended talks by Marta and Hugo have seen plenty of this, and they've been very effective in describing the issue. So here are the papers on which this presentation was based on. Some of these are in progress. Some of them are under revision. And thank you all for kindly joining the session.
Thank you, Antonio. Any questions, comments? Alessandro?
Thank you. Antonio, first of all, a wonderful talk. Well, let me come back to a comment that came out yesterday that Igor made to Giovanni Rebaudo talk, because this is something that you already said, talking about the predictive approach, that if we don't have consistency, then we can only achieve exploratory data analysis. So I'm interested in what you think about. Well, first of all, let me explain detail a little bit more. Sometimes, I mean, beyond exploratory data analysis, you could also be interested in, inference, some other inference, of course. So you can achieve parameter estimation somehow, but you could also be interested in clustering the individuals. Though with this, I mean, when you lose consistency because you use extra information, covariates, or something more, I mean, the computation for clustering, I mean, as we typically do, model-based, are not so straightforward. So I've been inspired by Amy Herring yesterday talk about the clustering using the generalized Bayes approach. So I want simply to have your opinion on that.
Yeah, I mean, I don't mean to be dismissive about that. I mean, it wasn't meant to be a diminutio of the finitely exchangeable case. Because I agree with you that there are some aspects of exploratory analysis that are very important, like clustering. I agree, they're very elegant and effective tools, and I think this is an area that is worth investing a lot of energies. So my only point is that if you think of prediction problems, then they are a bit limited. I mean, they cannot address that kind of problems. Of course, they are effective in other ways, And of course, it would be interesting also to study these finitely exchangeable structures in an approximation perspective, like Diaconis has done, for instance, right? Try to find the distance between a finitely exchangeable model towards the exchangeable one in order to motivate also its use beyond the exploratory data case, which is also, I think, very interesting, though I've never investigated it, but I think it's an exciting area of research as well.
Any other comments, questions? Victor, back there. You run, Victor.
Thank you. Wonderful talk. I was wondering if you can elucidate a little bit about the broader scientific application of these methods. So, for example, in species distribution modeling and so on, there's just so many factors and dependencies that we try to bring in, because when the ecologists and others are talking to us, they're saying, no, we have to account for this, we have to account for that. So how do you see this being embedded in hierarchical, traditional Bayesian hierarchical modeling? And also, can you comment on scalability? Because nowadays we are seeing about lots of variables, lots of big data.
Yeah.
So thank you so much.
Yeah, thanks. Very nice question. So this is, the applications we have been working on are those that I mentioned, so mainly with species sampling data or network models, especially more recently with multiple populations. And the problem there is that, unlike the exchangeable case, you don't have Bayesian estimators in closed form. So you need to rely very heavily on computational algorithms in order to make these models work in actual applications. Scalability is a problem here, in the sense that, dimensionality hurts. We have been examining simple problems, but I think there is a lot of work to introduce also, variational algorithms and several, stuff like this that eases the implementation of these models. Yeah, that's certainly another kind of area worth investigating. Thanks.
Any more comments? I think people want coffee. Yeah? So let's thank Antonio.
Thank you.